All right, I guess we'll get started here. Just down a little bit here. So I'm going to talk about malware analysis and automation with Binary Ninja, which is a new, relatively new software program. So we're going to cover, what is Binary Ninja, in case you guys haven't heard of it. Why Binary Ninja? A brief introduction to a malware family called PLUGX, if you haven't heard of it. Disassembly and intermediate languages in Binary Ninja, and then the automation of PLUGX string decryption using Binary Ninja. So who am I? I'm not in any way affiliated with Vector35, the company that is developing Binary Ninja, but I actually work for Carbon Black as of last Monday. So, yeah, a little bit new here. And I have my lovely corporate laptop because I haven't gotten my analyst laptop, so hopefully everything goes smoothly because I haven't had a chance to set everything up here. But I've been in the security industry for a while, doing some malware RE, some firmware stuff, digital forensics, iOS programming. A few years ago, I was at DC3 in the intrusions department doing defense network intrusion investigations, which is mostly reversing malware and then also sometimes system forensics. I just wanted to make some acknowledgments here. Everyone in Binary Ninja Slack channel is just awesome. It's a great community, but especially Josh Watson, who, if you don't follow him, he works at Trail of Bits, and he was an early adopter of Binary Ninja, like a lot of the guys and girls at Trail of Bits. There's a really good, you can't read it, I guess, but I'll have these links up later. But he's written some good blog posts about using Binary Ninja, and that's actually how I found out about it. So June of 2016, sorry, he wrote a blog post where they had actually used Binary Ninja to automate the processing of over 2,000 binaries for a CTF challenge, and it was pretty inspiring. So I was like, wow, what is this thing? And I ended up getting a license in October of that year to try it out. Also, Ryan Snyder, who works with Vector35 fairly recently, as I was doing this exercise trying to write my decryption script, I ran into a lot of problems, and he helped me track down what was actually ended up being a core bug that was affecting the disassembly. So, and then all the early adopters that have been really helpful in the Slack channel especially, and just really sharing knowledge on the platform. Also Jordan, who's one of the main guys that started Vector35, for help and support, he's always there. But also he gave me a big bag of stickers that I can give out to you guys, so you can see me after. So what is Binary Ninja? It's a reverse engineering platform that was developed by this company Vector35, released back in July of 2016, the first public release. It's got a linear disassembly mode, graph mode. The graph mode has disassembly mode, LLIL, and MLIL, which I'll talk about a little bit later. There's a fully featured hex editor, which I'll be honest was the main thing that I was using for the first probably year that I had it, because it's just awesome. You've got built-in transformations like you can encrypt and decrypt XOR with even single byte or multi-byte, just pasting the key in. It's great. There's also an open plugin architecture and the open source community plugin repository, which is up on GitHub. It's under Vector35's GitHub. There's community plugins, and then some of those are actually adopted back into the product after. There's also a very active community Slack channel, which is just great, even if you just want to hang out. They're just a bunch of great people. It's hashtag Binary Ninja, but they also do announcements, support. Anytime you have a question, you can get an answer pretty much almost immediately from somebody, whether it's one of the Vector35 guys or somebody that's in the community. A lot of the Trail of Black people, Trail of Bits people hang out in there as well. So why Binary Ninja? So what was my motivation? So I've been using this off and on since October of 2016 when I first got my license, and I've been an evangelist for them since then. But I realized, I'm not really using it in my day-to-day. I still fall back on IDA. And a lot of the malware analysts that I talk to, my friends, I'm like, they're like, yeah, I've kind of loaded up Binary Ninja and I'm kind of playing around with it, but I still just kind of fall back on IDA. So back in January, doing quarterly planning and stuff, I'm like, I need to come up with a project for this quarter. What do I want to do this quarter? And so I decided, I was like, I'd really like to just take some common malware analysis task that I do regularly and see if I can just do this end to end using Binary Ninja. Just force myself to just do it, not go back to IDA. So I was thinking about it, and I thought, PLUGX is a malware family. If you're not familiar, it's been around forever. First samples were found back in 2008. So, 10 years worth. And it's still kind of, even the first samples of it, or variations of the first samples of it, you're still seeing in the wild. So if you look in any of the kind of automation platforms, there's almost always a plugin or like a module that handles PLUGX, because it always follows kind of the same, or usually follows the same methodology. So these things continue, the signatures and decryption routines tend to keep working on them. So I thought that would be a perfect example to do for this. So I decided, I'm going to do kind of a history of PLUGX, which the blog is, I have a blog post up on my former company's website going over kind of the history of PLUGX and pulling together all of the kind of historical research over the last 10 years. And I thought, why don't I just take the simple string decryption, one of the first steps, it decrypts the API calls. So I thought, that's a simple thing, can automate that using Binary Ninja. And, why do I like Binary Ninja? First of all, IDA's a monster, not a monster, but, it's been the de facto tool for decades, basically. And so it's kind of nice to see somebody coming in and trying to shake up the industry. And just the progress that I've watched over the last 2 years, it's been amazing. It's a great team of developers. They're very responsive to the community. Anytime there's a bug or something that, a feature that people want to get in, they're right there. They're taking that feedback and they implement things very quickly. So it's really an agile platform. Also, the community support is just great. All the people that have adopted it, everybody wants to help, give back, and I've always had very responsive feedback to questions and things like that. And also, it's very extensible. The API is great. It's fully documented, which is great. It's actually readable and very easy to understand. So one of the things I talked about at the beginning was these intermediate languages. So Binary Ninja has its own intermediate language set of intermediate languages that they developed called Binary Ninja Intermediate Language. The first one is the LLIL, the lower level intermediate language, and then the MLIL, the medium level intermediate language. They're also developing an HLIL for a future release. There's no timeline for that just yet. But if you're not familiar with ILs, which I wasn't, honestly, I don't have a computer science background, to be honest. I came from math, so I wasn't familiar with this concept, but compilers actually use this intermediate representation to analyze and optimize code that's being compiled. And again, Josh from Trail of Bits, he wrote a really good blog post on breaking down the low-level IL. So it's a much more elegant overview of the IL for Binary Ninja than I can provide, but I wanted to get an overview as well. So these intermediate languages basically provide a higher level abstraction where you have the assembly that's translating your machine code into something that's more human readable. But anybody that studies or analyzes assembly, it's not super human readable. It's not real friendly. It's not like reading source code, right? So intermediate languages provide this abstraction that lifts the assembly up to something that reads a little bit more like source code. And I just put a quote up here from the actual documentation. They actually have a developer's guide for this LLIL, and it's a really good read that really helped me. They stepped through an example to kind of demonstrate what the IL is and how it works. So they said the Binary Ninja intermediate language is a semantic representation of the assembly language instructions for a native architecture in Binary Ninja. And they actually support quite a few architectures. And unlike, well, I'm not going to get into that, but everything is packaged, unlike IDA. It's not like you pay for different architectures in terms of like decompilation. So anyway, BNIL is actually a family of intermediate languages that work together to provide functionality at different abstraction layers. So that's just kind of a basic overview of these ILs. This is kind of a tangent, but I just saw this yesterday. Ben Demick, who was teaching the Introduction to Reverse Engineering yesterday, I went to actually get these stickers from him because he brought them from Infiltrate. He showed me this tool or website called Compiler Explorer. And if you haven't seen it, this is really great. So you can basically put in, this is C code, but it's got support for like 10 or 12 different languages. But you can basically put in source code here, and it'll disassemble it for you. But it also color codes, so like int sum equals 0, it actually color codes what the assembly instruction that corresponds to that over here. I just thought this was really cool, and it's, it's assembly, so it's slightly relevant. Anyway, back to this. So these intermediate languages, I wanted to just kind of give like a pictorial representation here. I know you can't read this, but we'll go into it a little bit more in the next slides. Basically, here's your disassembly, and the way that the intermediate languages work, just by virtue of their purpose, really, you end up getting kind of a condensation of code. So it's almost like an optimization-ish. So you can see that like on the lower level representation, this code gets collapsed a little bit. It's a little bit more compact. And in the medium level, it's actually even more compact. So I just put a few, like kind of a quick example of, here's like the disassembly, and then what that would look like in LLIL, what that looks like in MLIL. So you can see it's kind of, compressed. But let's look at it a little bit further. So here's the original disassembly that we were looking at there. And you can see you've got a move instruction up here. So we're taking the address for that function, release DC, moving it into EDI so that we can call it later, right? So this is typical call for a disassembly, in disassembly. The LLIL representation, we can see it looks a little bit more like source code. So you've got this the function address, and this .d is just indicating that it's a D word. So you'll have .d, .b. That's just a binary ninja representation. So it's actually just showing this is an assignment. EDI is getting, this address. And then it's a call EDI rather than, it's not a whole lot different, right? But semantically. So then, but the difference is you've got this jump here. So instead of doing, this move and then testing the register, it's actually going to look more like an if-else statement. So, if this condition, then we're going to jump here, otherwise that. So it just makes it a little bit more human readable, right? So LLIL versus the MLIL. So here we've got basically this whole set of instructions gets collapsed down here. You've got the call, basically they've collapsed instead of pushing these arguments onto the stack and then calling, you're just going to see a function call with the parameters. So it's just even more human readable. And again, similarly, this is kind of the same, but you've got the if-else statement rather than a conditional statement. So let's look at the original disassembly versus this MLIL. Again, you've got this whole set of assembly instructions that gets kind of collapsed just down into 3 lines. So it's a little bit less to pore through, makes it a little bit easier. So one of the things that is a little bit different with binary Ninja, is this concept of binary view. So when you first load a binary into Binary Ninja, whether it be from the command line, because there is a headless mode, I didn't mention that. It's not in the demo version. There's a free demo version, but it is in both the personal and commercial versions. But basically, when you load one of these binaries into the program, it's going to give you 2 different, so I'm just going to talk about x86 plain PE binary. It handles all sorts of, you can load Mako and, ELF files, whatever. But we're just going to talk about a PE here, since we're talking about malware. So there's this binary view module. And basically when you load into the software, for a PE, you've got raw mode. So basically you're just manipulating bytes in a raw fashion, kind of like, you're in a hex editor. Or you've got PE mode, PE view. So the PE view is going to give you a different set of APIs that you can work with this binary. So the very first thing that you have to do if you're going to automate something or use this headless mode, you have to tell Binary Ninja, what view am I working in here? And so the this binary view module has several methods. You can do, there's a binary reader and a binary writer. This is another one of my favorite things about Binary Ninja. Instead of, like IDA in the past when I would do something like this, let's say a string decryption, I have the binary in the editor in IDA, and you can perform this decryption routine, and then you have to patch back the database, right? You're patching the database and saying, okay, this string at this offset is now decrypted to this, and you can put like maybe a comment in there or something. But that's just in your database, right? It doesn't touch the binary itself. With Binary Ninja, you can actually write back to the binary. So I can say, okay, all these strings at these offsets, these encrypted strings, now I've decrypted them, now write those back to the binary. So now when I load that binary back into IDA or any other program, those strings are already decrypted, so I don't have to go and patch, put comments in or any of that. It's just going to fix the references, which is really handy. So you've got this binary reader, binary writer. Those are probably the most, sections, segments, references, and all that. So all this documentation is up on api.binaryninja.com, and kind of that standard Doxygen format, if you're familiar with that. It's very easy to navigate. So let's just take a look at the actual interface. Let's see if I can actually get this to behave. That's not what I wanted. Yeah, I've had this laptop for about 5 days, so. I like how the background extends. Yeah, I don't know. Shoot, I don't know how to get this new touch bar thing. It doesn't have the same options on it. Yeah, so I haven't quite gotten used to this. If anybody knows how to switch. Yeah, I need to show my Apple tab. No. No.
Oh, wait. No, do what you did again because the desktop bar shows up.
Ah, okay.
Maybe you can click it to switch to desktop one. No.
I was closer. All right. This is great. Yeah, right.
Just reboot your router.
All right, this is not going to be good here. Extend desktop mirror displays. Yay, okay. Woo! Okay. Yeah, I don't think I've used VGA in a while. All right, so basically, this is the main Binary Ninja interface. I've already loaded up a DLL in here. So this is our actual malicious PLUGX binary. But I just wanted to show the interface a little bit because honestly, when I first started using this program, the UI, I'll be honest, it was a little bit hard to navigate. They are actually completely redoing this. So this is version 1.1 point something. I'm on one of the developer builds. But version 1.2 has a complete overhaul of the UI. So I've heard about some of the features that are going to be implemented, but I haven't actually seen any of it yet. But it's supposed to be coming out sometime soon. So I don't know the exact release schedule, but this is all going to be kind of changed. But I did want to show it anyway. So like I was talking about before, we've loaded this up, and for a PE, it'll actually just default into binary view. I thought we were going till 11:30. No. Okay, I was like, oh my God, are you kidding me? Okay, so I was getting the 10-minute warning there. So anyway, so when you first load this binary into the interface, if it's a PE, it's going to default to this binary view, PE view, and load you into the graph view of the disassembly. But down here, there's hopefully you can see that all right, it's not too low. There's this menu down here where you can change to either raw view or PE. So we can actually switch to raw view, which is kind of like a like hex editor view, basically. So let's go back to PE view. And then you've got this other one where you can go to hex editor or disassembly graph. So you can see when I moved back to PE, it's still in kind of the hex mode. So you've got the disassembly graph, which is what we were seeing initially. You've got strings, which is just, the strings in the binary, obviously. Linear disassembly. So if we look at one of these functions here, this is going to be more like, just like IDA, which I'll mention also, if you're familiar with IDA, most of the key bindings are the same. So, your space bar will go between graph view and linear. G is going to be your go-to address, So most of these key bindings are the same. There are extra ones, no, I'm in linear now. If you're in graph, you can hit I to switch between IL modes. But you can also do it down here from this last option. If you're in graph view, so the low-level IL and medium-level IL are only available right now in graph view. A lot of us have been poking them and say, please put that in linear disassembly view because I don't like graph view personally most of the time. But so you've got your low-level IL view here and your medium-level IL that you can kind of switch between. But again, you can also toggle between those that way. Down here, you've got your XREFS. So I've got all the cross-references to this function just listed here, which is nice. You can actually hover over it, and it'll show you kind of a preview of it, which is nice. One thing I'll mention, though, you'll see there's 4 functions here. So one of the things that initially was a little bit difficult, these guys all the guys that developed this are kind of vulnerability researchers. So they come they use, IDA and these tools. They do very different reverse engineering than I do with malware analysis. So the features of the product initially were very much more geared toward using it for CTFs and VR stuff. But finally, I think it was last year sometime, they implemented in 1.1, they implemented linear sweep. So that made this a lot better. Because before, when you would load malware into here, a lot of times, if you're familiar with malware analysis, it doesn't always play very nicely with disassembly, and purposefully tries to trick you, or trick the disassembler and mess things up. So a lot of times functions wouldn't be defined automatically, so you'd have to go through and manually define functions, which again, the key bindings are just like IDA. You can hit Y to define a function at an address and all that. So anyway, so they implemented this linear sweep, and it's still a beta plugin right now, but you can actually run this analysis module, linear sweep. So if we run that on there, we see we get an extra function here that wasn't identified previously. So it turns out that this first function is actually our string decryption function. So once again, just like IDA, you can hit N and actually rename that. And then we see these XREFs down here. So all of these are going to be calls to this decryption function. So this is where we're going to find all of our encrypted strings. So if we look at this, let's go here. So here's this call. Let me switch back to regular assembly. So here's this call to the string decryption function. You see these, the parameters that are passed on here. We've got the address of our encrypted string. So let's just go there. So if we double click on that, we can see this, it's a little bit compacted here because of the screen resolution, but you can see you've got obviously most of these are not ASCII. So these are our encrypted strings here. And hit escape, go back here. So we'll take a look at this a little bit more, but just wanted to show you that real quick. And while we're here, actually, so I can hit Apple N. So here's our hex. This is actually the hex editor. So if we put in, we can just, whoops, wrong side. We go over to this ASCII side here. I can just type something. And just to show you the transformation here, You've got, if you right-click on this, you can actually copy as, these different types of strings and things. You can copy the raw hex, whatever. But this transformation thing is one of my favorites. You can actually, XOR this. You can RC4 encrypt it. If you've got, let's say you've got an XOR encrypted string, you can actually just hit this and give it the key. And like I said, you can just paste a whole, it can be arbitrary length, which is nice. You've also got encoding. You can encode this or decode base 64, which is great. So just a nice little kind of handy thing in there. All right. So let's see if we can. I'm mirroring displays, so hopefully this is okay. Let's go back to the presenter view here. So just a little introduction there to the UI. So what's PLUGX? If you're not familiar with PLUGX, it's a fully featured remote access Trojan or remote administration tool, depending on who you talk to. The first samples, as I said, were seen back in 2008, but it's still being used. A lot of the what's old is new again. There's a lot of code reuse in malware by malware actors. So this is certainly one family that, like I said, even the version, like the first variant, you're still seeing that in the wild today. So even though there's been a lot of code evolution over the last 10 years, and actually Palo Unit 42 recently, I think it was in January, they saw a new one that is completely different than all of these. They called Paranoid PLUGX, which is kind of interesting. But even despite that, you still see these original versions out there. So this original version typically follows this same kind of methodology. You have like a self-extracting RAR or a dropper that has 3 files embedded in it. You've got a legitimate signed executable, a DLL loader, typically that gets side-loaded by this signed executable, and then you have an encrypted shellcode payload. So the shellcode is generally, it's decrypted and decompressed, usually LZNT1, by this DLL and then injected into some legitimate system process. Usually it'll do, allow me to talk about that in a minute. So the sample that I'm using today for this demonstration follows this pattern. So what is side loading? For anybody who's not a malware analyst, in case you're not familiar with this, legitimate Windows executables or executables in general will typically, they rely on external libraries to do functions. You don't want to statically compile all of these things or rewrite all this functionality that's available in libraries, right? So at runtime, these libraries are loaded by the executable to perform, network functions or whatever the malware wants to do. But these executables typically don't do any sort of validation before they load these libraries. They just say, I want network.dll. Give me network.dll. And Windows will follow a chain of locations to find those DLLs. But malware can take advantage of this and say, because the first place that the binary is going to look for the DLL that it wants is in its current directory. So malware can just say, okay, you want network.dll, I'm going to give you my version of network.dll and put it next to you so that you load mine instead of yours, or the legitimate one. So basically, a lot of times, malware authors will use these legitimate executables are usually from something like antivirus or some security product, so that not only is it legitimate, it's signed, trusted by the operating system, but you might even take advantage of some application whitelisting that might not be on your system. So you might actually, your administrators, your network may have something like, let's say they've got McAfee whitelisted in the network. So not only is it going to be trusted by Microsoft, but it's also going to be whitelisted on the endpoint. So here's just a couple examples of some. The one that we're going to look at today is actually this ashield.exe, ashieldres.dll. So ashield.exe is an actual McAfee vShield component, the actual thing from the product. Similarly, you've got an F-Secure GUI component here. There was one that was a Office 2003 SP2 update file. So we've got our legitimate executables here, and then the malicious executables that are loaded. So how does this work? I mentioned that the shellcode is loaded and usually injected. If you're not familiar with process hollowing, this third component contains the encrypted and compressed shellcode and C2 configuration data. The loader DLL, this malicious DLL that gets loaded, will decrypt and decompress the shellcode. Like I said, it's usually, a lot of times it's LZNT1, and usually a simple XOR or XOR combined with some arithmetic in terms of the decryption. So this loader actually starts a new instance of a process, let's say like svc host.exe, but it starts it in a suspended state. So that program's not running. And then it'll actually go into this suspended process, free or unmap a section of memory, and then load the shellcode into this freed memory, set the execution to the beginning of the shellcode, and then start the process, resume the process. So the decryption method. So how do we identify this? If you're not familiar, probably most of you, if you do malware analysis, are familiar with YARA. They call it the pattern matching Swiss Army knife. But basically you can, if you're not familiar, you can key off of ASCII strings, or you can do regex, or you can actually specify bytes with wildcarding. So here, for this particular, this is actually the string decryption signature that I'm using. And there's actually two versions of it. So if you're familiar with assembly, you've got a like an XOR instruction. It could be one of two things: your move instruction, whatever. So we're actually going to have two different versions of these with different instruction disassemblies. But when you've got in your disassembly, a lot of times you're going to have a hard-coded offset or something like that. So you don't want to actually hard-code that offset because it's going to vary among different binaries. So you actually kind of can wildcard that out. So I can say 8A followed by 2 to 4 bytes somewhere in there, followed by another 8A, or 8B 2 to 4 bytes followed by an 8A, etc. So we're going to use this YARA signature, run it against the binary to find the offset of this decryption routine. Basically, it'll give us back the offset of where this code starts. So we get the offset of this decryption code. Then we want to say, okay, what are the cross-reference? Let's find the function that this code is in, get the cross-references to that function, get the parameters passed into the decryption function, because that's going to give us our key and our encrypted string and all that. And then we're going to decrypt the strings and then patch back the binary. So that's a basic methodology. Please excuse my Python. I am not a Python expert, and this was written rather quickly, so no judging, please. But anyway, so here we're going to see, I'm going to get the YARA offsets for this, we're going to run YARA against it and get the offsets. Like I said, again, this binary view, so the very first thing that you have to do when you start processing a file is to get this binary view object, because that's basically going to open the door to your API. It'll give you an object to work on, basically.
This is the binary ninja API.
Sorry?
Binary ninja API.
Yes, actually, I should have. Okay, so I should back up. Basically, in headless mode, you just import binary ninja as a library. So you've got your binary, you add it to your Python path, the whole binary ninja library, and then you can just import it like any other Python library. So you say import binary ninja, import from binary view, yada yada. So these methods are actually available to you once you import this library. So the very first thing that you're going to do is get this binary view so that you have something to work on. And the very first thing I did was run linear sweep against it so that we can make sure that all of our functions are analyzed or identified. And then you can update the analysis and wait. So it's just going to wait for it to finish running through that linear sweep. Then we want to get the XREFS. Again, most of the time you're going to have to pass this binary view object in. We're going to get the key and the other parameters. And then we're going to decrypt and then save this back out. So my decryption function is going to patch back that binary and then save it out. And you can save it out to, an external file of some sort. And I've got a useless print function in the bottom of that was probably from debugging. All right, so I'm not going to go through all this code, but I just wanted to show a few things in here. So the way that YARA works, you're going to get basically an array of hits. So if you've got multiple offsets for, let's say there were multiple decryption functions or something for some reason, it'll give you back a array of these hits. So you can basically just iterate through those. For each hit, then, you can match the strings, and I want to get the offset of that, and then the function that contains that offset. The XREFS, again, pretty simple. You've got this, in the binary view, you've got this get address for data offset. This is the other nice thing. Even though they're kind of long, sometimes to type out, it's nice that the actual functions and API, the calls that you're referencing are very descriptive. So get address for data offset. Pretty self-explanatory. We're going to take an offset and get the actual raw address for that. And so then again, get functions containing. So I've got my offset. I want to know what function contains that offset. And then I'm going to append that to these XREFs. Again, get code refs. So I've got the start of my function. I want to get the code refs to that. So very simple. Trying to do this in IDA Python would be a lot more code. Basically, I'll just say that. So we want to get the key. So this is where one of the things I wanted to go through, because this was something that I really struggled with. This is one of the things that Josh really helped me through, because working with IDA, if you've done something like this in IDA, you get your offset and then you're kind of like traversing back or traversing forward and looking at the operands and blah, blah. In this, because you've got that assembly level and you can do that, but you can also lift to IL and actually work with the IL, the instruction itself in IL, or you can go up to ML. And so it kind of took a while to wrap my brain around the way to, because it's a different way of looking at it, I guess I'll say. Rather than just saying, okay, go back, I've got my hit, let's go back, find the XOR call, let's go back, find the call to this function, get the parameters that are pushed, just kind of iterate back. Instead of doing that manually, you can actually do it kind of semantically, where you say, I've got this call to this function, it's got parameters, rather than, working kind of at the byte level. So for these offsets, let me go down here. So once you get, this is the other thing. If you're looking at the code, like I said in that graph view, so instead of just looking at an instruction view, you can actually go through with Binary Ninja, you can look at the blocks. So I can say this function block or this function block, and I can work on a function block rather than a whole function or like an individual address. So when I get the functions containing this offset, I can actually get the basic blocks. So I can look at the block that contains that virtual offset and get the low-level IL for that block. So I'm just going to say, give me the intermediate language, the low-level intermediate language for that block. And then I can iterate over that. So for every basic block in that LLIL, I want to look at the instruction index. And then for each of those those ILs, I want to look at the actual operations. So if there's an LL set reg and an LL XOR operation, then I want to say this IL source write is giving me the second parameter for that call. So that's going to be my XOR key. And I'm just appending that to my keys. In this case, there's only one, but in case you had multiple. The decryption, again, we're working at this IL level. So I can say, get the LLIL at this address, but then I'm going to actually lift up. So I can lift up to this MLIL. Now, right now, this was another confusing thing to me. They haven't fully implemented the API for the MLIL, so you actually have to lift up to LLIL and then up to MLIL and back. But in the future, we're going to be able to skip this and just get MLIL at the XREF address. But for now, we're going to look at this MLIL operation. So I want to see, I want to look for, is this operation a call? So if it's a call, then I can get my params. You've just got for this call object, you've got a parameter array. So I can say, okay, my encoded string is the first parameter, the string size is the second parameter, and there's like an arithmetic operation, that's the third parameter. So instead of saying, okay, what's pushed onto the stack before this, and having to know, okay, I know that there's 3 arguments, so I need to get this push, get those values, and come back down. This knows, okay, I've got a call, and that call has parameters. So you don't have to think about it, really. You can just get those values. This BR, like I said before, when you've got a binary view, you can make one of these binary reader objects and a binary writer object to read and manipulate the actual binary. So we can seek for that encoded string and actually patch back. You can write 8 bytes, basically, so patch back to the binary itself, which is great. This is just the encryption function here. Basically just an XOR, and then you're subtracting this one value, and then XORing and adding it back. Very simple. Okay. So I can't actually run the code because I can't get the environment set up on this corporate laptop, unfortunately. But I mean, you guys don't really need to see me hitting enter on a terminal window and then, you know, it's not very interesting. But I do want to show the result of this. So if we go back, this isn't going to work. I've got to use this. All right, so if we go back to the interface here. So I've already run this, my decryption script. So this is our original view here. And if we go to, so you can see here, this is our offset of our encrypted string. Oh, if you hover over it, unfortunately it's off screen, but it shows you the actual location in memory where this encrypted string is. So after I've run this script, I get this file written out, the modified binary. And let's go back to our string decode. Let's go back to our XREFS here. And down to the call. Oops, that's not the call. Go back here. So here's our call. And you can see instead of having just this offset there, we actually, it gives us the decrypted string. And I didn't have to, you know, in IDA, this would be like a comment or something that I manually wrote back to my database. But here, I've actually patched the binary. So as soon as it loads this again, it knows what's at that offset, and it just gives it to me. So we can actually look here. Let's look at this. So before we had, you know, these were all encrypted strings. But now we've actually got the decrypted versions written back to the binary, which is really handy. So I can actually take this this file that I've loaded in here and load it into any other tool, and this stuff is already patched. So I don't have to mess with it. As you can see back here, whoops. So here's our same region of memory with the encrypted. So very handy. All right. So I've got actually oops. Sorry, I'm really bad at PowerPoint. All right. And you're not going to be able to see these. But basically, there is a free version of Binary Ninja. The only real restriction, it's pretty much fully featured, but you don't get headless mode, so you can't do the scripting. But the personal version, if you're not using it for commercial use, it's like $129, I think, $99, $129 something. So it's, you know, unlike IDA, where I think my license was like $15,000 with the decompiler, 120, it's a little bit easier to kind of get into. Yeah, so, you know, it's great because I've heard just the last couple of days, I've heard that there's some universities that are starting to use Binary Ninja in their classes. So I think this really does have the potential to take off. I'll admit I'm not using it 100% for my complete workflow yet, but going through this exercise was really opened my eyes to how easily you can work with this API and the not only ease of it, but it's very robust. So, I really think that it's got a chance to take off. But even the commercial version is only $600. So, and the support, you just go into the Slack channel, and there's tons of people that are just willing to help and get answers and even patches. When RSS, or the guy that Ryan, when he found the bug that when I was in the disassembly and identified it, it was, a few hours later, he was like, oh, okay, that's fixed now. So you're good to go. We're going to push that out in the next dev cycle, or the next dev release. It's like, great. So I just have the community plugins are on Vector35's, so it's github.com/Vector35. That's where you'll find the GitHub and the community plugins and all that. A lot of this code is actually open source. So if you go to the, let's go back here. I don't have internet access, but I did load this beforehand. Oh, this is another, Josh really has, if you're interested in this, I would definitely go to the Trail of Bits blog. He's written some really good blog posts explaining, this is the one that I mentioned earlier, explaining the low-level IL. So it's actually a tree structure. This is the way that they did it. And it goes into more detail in the developer guide, which is here. So this developer guide written by the Binary Ninja guys kind of explains, here's, the lifted IL, low-level IL, mapped medium, and then the future high level. And they just kind of go through an example to walk you through what it means. This was very helpful for me, not knowing what intermediate languages were initially. And so they talk about that tree structure. So in this case, this is a load effective address. So we're loading EDX plus ECX times 4 into EAX. So the way that works, we've got an LLIL add, so we're adding source and dest. This ECX times 4 is actually going to be a shift by 2. So we've got this LSL shifting ECX by 2, and we're going to load that into EAX. So it just kind of gives you a pictorial demonstration of how the LLIL works in this tree structure. But that was not what I was going over here for. What was I talking about? GitHub, thank you. That's YARA. No, that's not. Okay, I don't remember what I was talking about. Josh has thrown me off. But anyway, yeah, this documentation is very good. Oh, this is what I was talking about, the API documentation. So I can't actually load it, but any of these modules, you can actually see the source for that. So there have been a few times where, they didn't necessarily give much of a description. Some of these things actually have a good description, like this analysis completion event. You can see it gives you a good description of what this module is doing. But if you need more, the source is actually there, which is nice. So you can actually verify things. And a lot of these actually have, I can't scroll sideways, but there will actually be examples, which is nice. Nice change, I'll say. All right, so we've got about 10 minutes left. I wanted to leave some time for questions because I know, I had a lot of questions when I was first doing this, and like I said, the Slack community was just amazing. This is my contact info, but Gutter Churl on Twitter, and feel free to email me as well. But does anybody have any questions? Yeah.
Yeah. You mentioned the workflow with binary and IPRO too. Are you finding that you kind of develop a new workflow where I'm going to get through binary real quick up to a certain point, and now I've got this hash binary that I just binary engine. I can feed you the IDA.
Yeah.
So what kind of use cases where is it?
Yeah, so he was asking, how is this going to change the workflow? Basically, are you using is it going to change the workflow? I'd say, yeah. A lot of times with IDA, I'll just load the binary up and do some static analysis. But with the ability of the API, one of the things I think I mentioned before that Josh had written about back in 2016 was processing like 2,000 binaries with this. So, you know, a lot of times the initial will probably be the same. You know, I'll load up this PLUGX sample and I need to find the decryption routine, right? But once I identify that, instead of in IDA, you know, maybe writing YARA signature and finding some other samples or something like that, you can very quickly write up one of these decryption or script like this to run against, if let's say I run a retro hunt or something on VirusTotal to find a bunch of samples, then I can very easily process a large number of samples. Whereas before, you know, it might have, you know, I'd run YARA manually and I might write the decryption routine for IDA Python, but it would take me a lot longer. You know, I don't know if that really answers the question, but, you know, I guess I'll say that it's not exactly, like I said, it's not really in my day-to-day workflow just yet. So that's probably going to change once I get a little bit more comfortable with it. But I really wanted to, because people were saying, you know, I've kind of played with it, but I don't really know how to use it. I really wanted to go through this exercise just to say, you know, it's really not that scary. It's not that hard. There's a lot of help out there. I felt very shy about asking for help. You know, the whole imposter syndrome thing. It's like, you know, I don't know what I'm doing, whatever. But everybody was very supportive and very helpful, and really just wants to they just want to get more people using it and build that community so that we can all work off of each other. So it was a really good exercise, and I hope that maybe you'll take a look at it and play around with it too, because the more people that are using it, the more people we have to bounce off ideas and, you know, help to solve problems, you know, when they come along. So, any other questions? Yeah.
Search through a binary using the intermediate language. So, like, let's just say, like, you didn't need to use YARA. Like, I understand why you can use YARA with, like, virus.
I know you hate YARA, but...
You like search up the binary, like, for, like, the decryption function or decoding function you had. Can you, like, specify a sequence of, like, IL instructions and then search?
Yeah, I mean, you definitely could. So he was asking, instead of using YARA to identify the decryption routine, can you use the IL to actually say, you know, search for like a set of instructions? And I didn't really think about that. That kind of gets back to my point initially, where when I went into this, I'm still in that old mindset of, you know, this is how I've always done it. And so having to go through the IL really opened my mind to, hey, I have to think about this differently. And so I hadn't really thought about using the IL that way, but that would certainly be potentially more elegant than YARA, which can be, they call it the Swiss Army knife, but, you know, sometimes you're using a knife to kind of hack at something until, you know, you get it to work. So, so yeah, I hadn't thought about it that way, but you certainly could, because you've got, like I said, in that LLIL call, you just go back to, you've got these MLIL operations dot, you know, MLIL call, add, you know, all of those things. So you could certainly, like, you know, set up an array or something, or I can't think off the top of my head how you do it, but if you're just looking for a pattern of push call or something like that, you could certainly do that and then get the XREFS. So yeah, that's a good idea. Any other questions? I think we're almost out of time here. Yeah. Or if you want to, you can see me after. I've got stickers. So, thanks.